Color is light. That's it. Light is just roaming around. It hits something like a banana, then gets reflected off to our eyes, and that's how we see the banana to be yellow. But like, why is it yellow and not a more suiting color like blue? Well, that has a lot to do with what's happening here. So we know that color is light, but what's light itself? Isaac Newton had that question too. So he used this process you see here called prism and split white light into 7 colors. These colors are basically different waves, each with a different length. So that's what's happening on the light side. But on this side, the banana has these chemicals on it called pigments. These pigments treat the wavelengths or colors in light in different ways. Like it absorbs all the wavelengths except the yellow one, so it basically reflects it. And that's the color we see bananas. Kinda sad though, imagine becoming what you don't want. Now just like bananas, almost every object has pigments on it. These pigments could be really common, like green from plants, or something ultra rare like the ultramarine color coming from a certain type of gem. So throughout history, we extracted these pigments and tried to recreate natural objects in our paintings. All we needed was at least 3 colors: red, yellow, and blue. It's all a game of absorbing and reflecting. If you want to mix red and yellow, you list what each of them absorbs and what it reflects. The resulting color is what they reflect together. So this means that everything reflects a certain light, and that's how we see it. Like pink stuff reflect pink light, right? This is where it gets tricky because there is no pink light in the spectrum of visible lights. So how do we see pink then? The answer lies in another place we haven't considered yet: our eyes. We see color thanks to these cone cells inside our retina. When the light that's reflected from something hits our eyes with a certain wavelength, it triggers this area with 3 types of cone cells, each sensitive to different wavelengths. Like this S cone is sensitive to lights with short wavelengths like blue colors. The M cone responds to medium wavelengths like green, and the L cone responds to long wavelengths like red colors. So each responsible cone cell picks up a different one and sends a signal to our brain. And there the lights get mixed and matched and ultimately interpreted as one color. So the funny thing is that our eyes don't work with a red, yellow, and blue model we used earlier to mix paints. It works with red, green, and blue, or RGB instead. Every color gets translated into a little bit of green, a bit of blue, or some red. And true white light like sunlight triggers all of the cones, and pitch black triggers none. So with all that said, we can perceive way more colors than exist singularly in visible light. Colors like magenta, pink, brown, and purple basically don't correspond to one single wavelength, and we can only see them thanks to this power of our eyes and brains. But every eye is different. One eye has a more sensitive M cone, while the other has a more sensitive L cone. And sometimes one type of cone might not work well, which is exactly the cause of colorblindness. Either there is no red cone cell, or green or blue, or there are anomalous cone cells of each type. That's how cats can only see yellows, blues, greens, and grays. Based on this whole thing, Goethe enters the story and releases a diss track to Newton, saying how Newton's ideas were all based on light and stuff, and color is actually subjective. Cause what about us? What about what we perceive? Why do we feel good when we see something blue but feel excited at the sight of something red? So he came up with a new color wheel that explored the idea of color harmony that we've been using in art and design for centuries now. But the thing is, that is not good enough for making realistic recreations of life, which peaked in 1800s thanks to photography. But as none of you remember, photos were all black and white back then. And so began the quest for recreating color as we know it. One of the first methods they used to preserve photos in color was to paint over them with dyes and pigments. But as you can imagine, these colors were very different from the real scene, and pretty inconsistent from copy to copy. Plus, they would fade away in time. So we needed a better method for preserving colors as we see them. There, that's the clue. And the second method, how we see colors. That got Maxwell thinking. Well, just like human eye, if we took 3 pictures of the same scene with 3 colored filters of red, green, and blue, then every photo would capture that specific color information and output it as a black and white photo. Then we could shine red, green, and blue light at each and mix these images. The result is pretty similar to the original scene. Thomas Sutton used Maxwell's method and managed to capture the first colored image. A lot of more people followed from the east to the west, capturing high-quality colored images. But one thing you noticed so far is that every method for recreation followed a model. In art and painting, they used RYB, which works by absorbing certain lights from white light and reflecting others. This is called subtractive color mixing. In photography and capturing light, they used RGB, which works by adding red, green, and blue lights to make new colors. So if you mix all the colors, the result is white. This is called additive color mixing. Subtractive, additive. It should be pretty clear to you by now that we're working with math here. So we know how to recreate colors with math, but based on these maths, what are all the colors that our eyes can see? Is there like a map? Well, not until 1931 when a bunch of color nerds in the International Commission of Illumination, or CIE, started recording the behavior of our cone cells and how sensitive each of them is to different wavelengths. The results came back in a diagram. They called this the XYZ diagram. Then they tried to map how each of these wavelengths on the diagram mix with each other and what colors are generated from them in total. And this was resulted from that. A bubble that mapped all the colors. We call this bubble a color space, and this diagram a chromaticity diagram for the XYZ color space. So now the only thing that matters is coming up with a map that is the closest to how our eyes see colors. While the CIE XYZ 1931 color space was pretty good, and still is the standard color space we compare everything to, it wasn't really accurate in the way it mapped lightness. And lightness here doesn't equal brightness or luminance or the opposite of being heavy. It just means how light or dark your eyes see a color. For example, on this spectrum of colors with the same coded amount of lightness, you're gonna feel like this color is actually lighter than this one. And this is because our eyes don't see every color at the same level of brightness. If I turn the 3D version of the CIE 1931 chromaticity diagram, you see that they all reach the same lightness in the end, meaning that it's not perceptually uniform. To fix this, they came up with another color space that was more perceptually uniform, called CIE Love. The L stood for lightness, U for the green to red amount, and V for blue to yellow. This CIE 1976 chromaticity diagram is a bit more perceptually uniform than the previous one. They specifically used CIE Love in light design or TVs, but for photography, textile, or graphic design, they came up with CIE Lab. Again, L stood for lightness, A for green to red, and B for blue to yellow. As you can see, the color measurement in these two spaces is completely different from the RGB space. RGB was based on the 3 types of cone cells, but Love and Lab are based on the opponent process. So you know how if you look at a red dot for long enough, and then if you take it away, you'll see an after image that's kind of green? That's a good representation of the opponent process theory. This theory suggests that our brain processes colors in 3 channels of green, red, blue, yellow, and black, white. And that's exactly what CIE Love and CIE Lab use. But the problem with these two is, well, what does 60 lightness, 50A, and 20B even mean? You can't really imagine the color. To fix that, they came up with another color space called LCH. L stands for lightness, C for chroma, meaning how colorful or colorless it is, and H stands for hue, or the essence of the color, like red, yellow, green, and so on. In this space, if I just tell you the hue, lightness, and chroma amount, you might just be able to imagine the outcome, which makes LCH much simpler to work with than Lab or Love. A more improved way of representing LCH was stretching all the chroma values to be from 0 to 100%. They called this perceptually uniform cylindrical space HSLUV. By now you've seen lots of different color spaces: RYB, RGB, XYZ, Love, Lab, LCH, and HSL. Each of these are actually a type of color space that have many more derivations trying to achieve a better version of the main color space for different purposes. Speaking of purposes, let's see what happened to photography after all these new color spaces were created. Since the RGB model, it's definitely gotten easier to capture realistic photos. Modern cameras work similar to the old ones with the RGB filters and everything, except instead of 3 RGB filters, here we have a color filter with repeating patterns of 25% red, 25% blue, and 50% green, because our eyes are more sensitive to green. Then the images go through a process to recreate the exact lighting of the image, or maintain white balance. Because white light isn't really white. You've definitely experienced taking photos of something under yellowish or bluish light. That yellowness or blueness is basically the temperature of the light source in your environment, and we measure it in kelvins. Yellow light like lamps are about 2000 kelvins, and bluish shades are all the way up to 10,000. We compare these white color temperatures to sunlight. So the standard daylight white is around 6500 kelvins, aka D65. The camera has to measure the existing light and apply the same white balance. Then it has to convert the colors to the proper color space to make sure they look consistent everywhere. But that's not enough, because it still has to create an image as close to what we see in real life as possible. So it plays around with color or lightness values. We can do that too in editing software by trying different color settings, so this media not only looks real but looks the way we want it to look like. This process is called color correction. But there's another obstacle between us and realistic color recreations: the amount of light that's reflected from every object, aka luminance. Our eyes don't see every level of luminance the same, especially not in different colors. So luminance for us is not a linear thing at all. But for cameras, it is mostly linear, so images turn out looking like this. Good thing the camera company applies a function that processes the image to have more realistic brightness in different areas. This process is called gamma correction, and this is called a gamma curve. This linear one has a gamma value of 1, and this one 2.2, which is the standard gamma value on cameras like on iPhones or most other interfaces. Now that we have some media, let's show them on a display. Okay, well, unfortunately, this little display sucks at showing the colors. Why? Well, it all goes back to its smallest building block, a pixel. A pixel is usually divided into 3 subpixels. You guessed it, the red, green, and blue mix together in different amounts and become one color. But the thing with these subpixels is that they need to save the color data inside bits. Each bit has 2 values, 0 and 1. 0 is the lowest intensity of that color, and 1 is the highest intensity. This display has 1 bit per channel and 3 bits in total, so we can show a total of 8 colors. As we increase the supported number of bits, there are more shades of red, green, or blue between the black and the pure color. So for example, a 24-bit display that has 8 bits or 256 colors per channel has about 16 million colors in total. And more accurate modern displays have a 30-bit color depth, which means 10 bits or 1024 colors per channel at about 1 billion colors in total. And 1 billion colors looks much more realistic compared to only 16 million colors. You can go even higher than that, to the point that if you compare an apple in real life with an image of it on a display and measure the color on the same spot, the color difference, or the scientific term delta E value, is going to be extremely close to 0, which means identical. So remember these as a sign of a good color accurate display. But all of this depends on the display technology. We've been through so many of those, from CRT to micro LED. CRT displays have a screen filled with phosphor dots in a pattern. Every pixel has 3 of these phosphor dots. At the very back, there's an electron gun for every color. So when they shoot an electron, the specific dot glows and their combination creates a single color. The colors they create are pretty accurate. They show the same color from every angle, and they have astonishingly fast response times. The downside is that they are ginormous and consume a lot of power. To fix all this, they created LCDs. They are smaller and don't use as much power, but there is a price to pay: color accuracy. LCDs use a huge backlight that's always on. They move these liquid crystals to block out some of the light and let the other light go through a filter of RGB colors. And that's how colors are generated. But the backlight is always on, so there is no true black, and the colors are way more washed out. Plus, because these liquid crystals have certain directions, the colors are not always the same from every angle. So LCDs have to go, and enter LEDs. Instead of a huge uniform backlight, every pixel has a diode that emits light. So the intensity of the lights determine the color of every pixel. This sounds great and all, but there are several problems with LEDs. 1, the colors are not always accurate. 2, the LEDs are usually kind of big, so this limits high screen resolutions and better picture quality. Because of all this, they came up with OLED displays that use organic compounds instead and emit light in response to electricity. Every pixel can be turned on and off on its own, so we can experience true black and amazing color accuracy. Another recent technology called qd-oled uses semiconductor particles, aka quantum dots, that emit red, green, or blue lights. They would use a backlight like in LCDs, but blue. This blue light hits a layer of quantum dots and turns some of them green or red. This gives the display an even higher contrast and brightness. But let's go even higher than that. There is still a big blue backlight. Why not just use the same organic compounds in OLED to emit blue light to each pixel individually? This way, every pixel could be controlled separately. They called this qd-oled, which is currently an astonishingly good technology for realistic and accurate colors on TVs. All these technologies throughout the years came together and tried to recreate the colors in every color space. The most common color space back in the 90s was RGB, so the International Telecommunication Union decided to release a standard color recommendation for high definition or HD TVs and monitors under the name Rec 709. Remember the chromaticity diagram? Rec 709 supports about 35% of the colors on the diagram. But because the brightness on these displays was mostly optimized for TVs and not offices, HP and Microsoft got together and released a standard RGB color space with a normal gamma value of 2.2, so it would be a bit brighter than 709. But colors on both sRGB and Rec 709 displays look a bit faded. Luckily, a Adobe released another color space that expanded on the cyan and green areas compared to sRGB. So the greens here are way more saturated, while the sRGB green looks more washed out. Adobe RGB covers about 52% of the visible colors. Now, if sRGB was common for the web and Adobe RGB was intended for printing, then blockbuster movies on big cinema screens certainly needed accurate colors too. Because of that, a bunch of big Hollywood studios got together in a digital cinema initiative and released a color space that gives you more vibrant reds and greens, covering about 53% of the chromaticity diagram. They called this DCI-P3. But unlike the other color spaces that use a more neutral 6500 Kelvin white point, DCI-P3 uses a 6300 Kelvin white point, which is a teeny bit yellower, like a very tiny amount. Apple followed after that and tried to optimize this DCI-P3 for their own displays to have a standard white point and gamma value. Soon after that, a much bigger color space was released as the new standard for ultra-high definition TVs. This one covered about 75% of the chromaticity diagram, and that's why they call them white color gamut displays. But all that is still not enough, because all these color spaces aren't bright enough to support the actual luminance perceived by human eye. The unit for luminance is candelas per square meter, aka nits. All these displays and color spaces so far supported only up to 300 nits, which makes colors look faded like this. They call this the standard dynamic range. But then they came up with high dynamic range, which supports up to 10,000 nits. With this tweak, the brightness of certain parts of images and videos would look much more natural. Just comparing SDR and HDR, you can tell the black is deeper, colors are way more vibrant, highlights are brighter, and shadows are darker. The images have more depth to them. Now, this is a good opportunity to come up with a new color space that supports HDR. So they took Rec 2020 and updated it to Rec 2100. So what's your display's color gamut? If you're not sure, you can usually go to the manufacturer's website under tech specs, or test it on this website. But let's get a little more specific for a second. Look at this website. It lists the same color in different color spaces. So here it is on an sRGB gamut display, on a P3 display, on a Rec 2020 display, and HDR display. The more difference you see in the colors of every column, the wider your display's color gamut. And the fewer colors you see, well, the smaller the gamut. Here's why. Let's say your display's color gamut is a canvas and the color spaces are sets of paint. In the sRGB gamut, there are less sections to draw, so even if you have the Rec 2020 or P3 paint sets, you'd only need the sRGB paint to draw the whole canvas. In the white gamut, though, there are more sections to draw, so you'll have to use colors from all the paint sets. And if you compare, the canvas with more sections in it looks more vibrant and detailed. You know what? This analogy reminds me of how much I love learning complicated things in simple ways. Like learning science by fun examples and playing around with different concepts and solving cool problems. Isn't that brilliant? It really is. No, I mean it. This is Brilliant, the sponsor of this video. Brilliant has lessons in math, computer science, tech, and much more, created by real pros in each field. And you're constantly solving things to really understand the concepts. I got to learn how to put the color knowledge from this video into use thanks to their creative coding course. And the best part is I get to go back every day and continue this coding path, learning something new and, of course, compete in a league with others, instead of doom scrolling all day. And that's just one of the paths. There's something for everyone on Brilliant. You can try it yourself for free for a full 30 days. Just visit my link or click on it in the description. You can also get 20% off an annual premium subscription. You know what else you can get? Better colors. So here's my quick display guide on things that I wish I knew before buying or setting up a new display. Generally, your budget sRGB display should be enough, but don't forget to look in the monitor's display settings. There might be a lot of things that you can tweak and improve your experience, like brightness, gamma value, and even color temperature. You can adjust them until you're happy with the result. But if you want to feel like you're there when you're watching a movie or playing a game, then you will need a wider gamut display like P3 or Rec 2020. It really makes immersive experiences even more immersive and realistic. But when it comes to creative work, you need the whole package. Speaking of creative work, let's talk about manipulating colors. If you've lived on Earth long enough, you've seen things like this. And a huge part of all this is color. That's why these look normal and these look cursed. Designers, artists, and marketers use their natural or acquired reactions to color to attract us, make us form an opinion, or manipulate us. Sometimes in a good way, sometimes in a bad way. We generally feel calmed by natural colors like green. So there's no harm trying to market a brand like that. But it could also be associated with disgust or envy. We feel like blue is more reliable, friendly, and high quality. or corporate and serious. Orange might seem tough and clean, or exciting and fun. Or we started associating brown and golden colors with warm aromatic bread. We keep seeing red in all sorts of places related to danger or extreme emotions, so it draws our attention. Or we learned throughout the years that a yellow colored drink is probably lemon, orange, or pineapple flavored. But someone in Japan might feel like this is a golden grape drink instead. So there you go, that's color psychology for you. But is it always accurate? Baffled by the accuracy of color psychology, I decided to ask some questions on my channel, and I got some interesting answers. Say these were all eligible options for a brand's color. Which one do you feel more comfortable with or connected to? Very random colors here, I know. And everyone had different feelings about them. But I wasn't looking for a winning color. I was looking for opinions. Blue is too corporate-y. No, green is. Green feels like nature, so it's more friendly. No, actually blue feels like nature and therefore more friendly. But most importantly, they associated them with brands and decided based on that. Like they refused to vote blue because even though it symbolizes trust, untrustworthy companies tend to use it. Crazy competition between blue and green, but in the end, as I suspected, green won. But then I changed the order of choices, and this time, blue almost won. Why? Maybe because green wasn't the first choice anymore. And suddenly, orange looked better because it was the first choice. Or maybe because the nearby colors were different and it made blue look more harmonic. There could be a lot of reasons. In light mode, everyone felt different, and blue won. Maybe because on a light background, this blue feels more contrasted than green. Alright then, how about we make the green slightly darker? Oh, okay, great. So does this mean green won, or... No, it doesn't mean anything. These colors on their own don't mean anything. Color psychology needs context. Either there is a context, or a context will be forced on a color. Based on context, there are ways to tell how everyone might react to colors. Besides, there are principles that we can use to make designs look good, like how only a slight increase of contrast made green win. Many people studied this relationship colors have with human emotion, and they all kinda agreed that some colors look better next to others. A cold color like blue makes a great combo with shades of red, orange, and yellow, or green goes well with shades of purple, pink, and magenta. These are some examples of different complementary colors, and they're used a lot in fashion. We could use the shades of the same color in one design and it would be a monochromatic minimalist design. We could also use no color except black, white, and grays, and that's kind of a recent web design and product design trend. Oh, and if we choose colors right next to each other on this color wheel, they would also look pretty good. We usually use this color wheel to generate schemes and shades of different colors. But what is this wheel? We really haven't seen it before. Well, we did see the HSL UV color space before, but this one doesn't seem similar to it. And that's because HSL UV is a variation of the LCH color space. This one though, it's a variation of the RGB color space. Yeah, it sounds confusing, but if you focus on the consistency of lightness across the two wheels, you'll see that the perceptually uniform one with the same level of brightness all around it is the LCH based one, and the non-perceptually uniform one is the RGB based one. And this one is called HSL. Just HSL. While HSL does work well for making color palettes for artwork and design, sometimes it just doesn't make any sense. For example, based on HSL, if we created different shades of the color blue towards white, you'd see that it slowly turns to violet. This is called the Abney effect. It happens the same way with red and green too. So basically the math might be mathing, but not in our eyes. So we need a perceptually uniform color space for our color manipulation. CIE Lab was good, but a newer version came out which is more okay in terms of perceived lightness, and it's called OK Lab. This one was the best yet, but it had a huge problem. The same problem that led to the creation of LCH. Lab is not as readable as LCH, so they created an ultra-accurate color space called, you guessed it, OK LCH. Even though I would say it's better than just OK, maybe Super LCH or Giga LCH, but okay. The same shades look much better with OK LCH now. They preserve the blueness till the very end. And let's say we create a gradient between two colors in different spaces. OK LCH still gives a more uniform result. And it's actually very good at recreating colors supported by the P3 color space, which is exactly why I'm using it everywhere for a while now. And so should you. But generally, how do you come up with the most good-looking palette? And then, how do you put that in your work? That's probably the most common question in this field, and it's pretty subjective. But if you follow some principles and take your color choices through several filters, you can find your winning option. First, does it fit the industry or context? This isn't that important unless it truly doesn't fit. Second, does it fit the purpose? For example, a saturated pink really isn't a good option for interior design. Just trust your gut. Third, does it fit the background? If it's on the web, does it look good both on dark and light mode? Fourth, is it too light or too saturated? Maybe it would look better if you muted it a little bit. Fifth, Which colors on the color wheel look better next to it? 6th, are the other colors contrasted enough with it? You know, so they don't look like this. If they don't contrast well, then modify them a little bit. Now let's say you have a winning palette. Obviously, your main color becomes the primary, most used color, and the others go next. I know it sounds like a lot of trial and error, but worry not, because you can do all that on this website. There's palettes, shades, different templates to test the stuff, and when you settle with one palette, you can export the values in 1,000 different ways and paste them in your favorite tool or in your code. The world of colors is pretty colorful, and you can truly get lost. But I hope now you have a better outlook at this underrated aspect of our lives. Well, that's all for this video. If you liked it, make sure you do your magic down below, and see you on the next one.